Ever wonder how AI models like GPT or BERT understand language so profoundly? The answer lies in a revolutionary architecture that's reshaped the field of machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, exploring how self-attention mechanisms, positional encoding, and parallel processing Chinese letter traditional neural networks. If you're a developer, researcher, or just curious about the engines powering modern AI, this is the breakdown you've been waiting for. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical limitations. RNNs struggled with long-range dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields that couldn't capture global context. Imagine trying to parse a 1,000-word document with a model that can only focus on a few words at a time. This is the bottleneck these architectures faced. Enter transformers, which abandon sequential processing entirely. The transformer's breakthrough is the self-attention mechanism, which allows the model to weigh the importance of every token in a sequence relative to others. Let's break this down mathematically. For a given token, the model computes three vectors: queries Q, keys K, and values V. The attention score between two tokens is calculated as the dot product of their Q and K vectors, scaled by the square root of the key dimension. This produces a matrix of weights, which are then applied to the V vectors to generate a context-aware representation. This is the essence of global attention. A token can dynamically focus on any other token, regardless of distance. But wait, how does the model know the order of tokens? Unlike RNNs, transformers have no inherent notion of sequence. The solution: positional encoding, a technique that injects information about each token's position into its embedding. This is done using sine and cosine functions of different frequencies, ensuring that the model can learn relative positions. For example, the positional encoding for position I$ and dimension d is defined as \text p I2k \sin \left frac I10002k /d \right \text p I2k plus 1 equals \cos \left frac I10002k /d \right. This allows the model to distinguish between cat sat on the mat and mat the on-sat cat without relying on recurrence. Transformers are built on a stack of encoder and decoder layers. The encoder processes the input sequence, while the decoder generates the output. Each layer contains two sublayers, the self-attention mechanism and a feed-forward network. Crucially, these sublayers are followed by residual connections and layer normalization, which stabilize training. The decoder also includes an additional attention layer to focus on the encoder's output, enabling tasks like translation or text generation. One of transformers' greatest strengths is their ability to parallelize computation. Unlike RNNs, which process sequences step by step, transformers process all tokens simultaneously. This is why they scale so effectively to massive datasets. For example, a 1,000 token sequence can be encoded in a single forward pass, whereas an RNN would require 1,000 sequential steps. This efficiency, combined with the self-attention mechanism, makes transformers the backbone of state-of-the-art models today. Transformers aren't just another neural network architecture, they're a paradigm shift. By decoupling sequence modeling from recurrence and embracing global attention, they've unlocked new possibilities in NLP, computer vision, and beyond. As research continues to refine these models, whether through sparse attention, efficient variants like longformer, or hybrid architectures, the future of AI looks more powerful than ever. If you want to stay ahead in this field, understanding the transformer is no longer optional, it's essential. Got questions about how transformers handle specific tasks, like code generation or multilingual processing? Drop them in the comments below. And if you're ready to dive deeper, check the description for links to the original paper and my next video on optimizing transformer efficiency. Thanks for watching, stay curious, and keep pushing the boundaries of what AI can do. Subscribe for more deep dives into AI research, and hit the bell so you never miss a breakdown. See you next time.